You guys heard of piecewise functions? Maybe you have. Anybody, raise your hand if you've ever heard of a piecewise function. No. Okay. Maybe a little bit. Okay. But not probably. If you have, I bet you haven't done a lot with them. So we want to learn what they are first of all, how to evaluate piecewise functions, and then how to graph them, and then eventually I'll talk to you about how you can use technology. They're still working on my TI-84 emulator, so when that's fixed, again, we'll come back and I'll show you everything that we've done that we've missed out on the TI-84. I'll take a day and just show all this stuff to you on the TI-84, but I will show you today on Desmos. And then if we get to it, we'll maybe look at just a couple quick applications of this kind of thing. So first of all, just to set the stage, this is, I love talking about this stuff in an honors class. You guys are headed in the direction of, math-related stuff. And so let's talk about math modeling, because that's something we do a lot of. So I just cranked this out this morning. I just want to show you an example. This looks complicated probably to you guys right now, but by the time you're in AP Calculus, this will be simple stuff, not a big deal. One of the most common applications of math involves modeling. That's what we do. We use math to create models that make predictions, and one good example is projectile motion. So this just has to do with projectile motion. I'm not going to go through the algebra with you, but you can look at that later if you want to, but I want to just show you how valuable math can be. So if we pull up, I want to pull up an example here. Oh, what did it do? Let's see. Oh, here we go. Yeah. This is what I want. This guy. Okay, we're just going to have a little fun here. We're going to play with the simulator. Projectile motion simulator. And so the idea here is just to maybe we'll start off by, we'll just kind of drag this to some place, like, I don't know, just arbitrarily. I'm going to drag the target to some distance away, and we're going to set the initial speed at, I don't know, whatever you want to say. We'll just arbitrarily say 22. Makes no difference. You can change that later if you want to. And let's see if we can't pick an angle where I can shoot a projectile and it'll hit the target. Anybody want to take a stab at you just take a guess here? I mean, you don't have any way to just, it's just intuition. What do you think? Who wants to play? Pick an angle for me. Wesley, pick an angle. What do you think? 70. Okay, that seems like a pretty reasonable angle to me. Let's try 70. So if we shoot this thing at 70, how'd we do? Oh, you missed. Okay, different angle. What do you think? 85? Okay, let's try 85. Let's try 85. Oh, we came up short. I'll tell you what, let's use math, because this could take a while, right? So let's use math. Let's go back. Let's go back to here, and if we could just do some relatively simple math here and come up with some models. Okay, I mean, it just involves a little trig. You guys haven't really done much with trig, so it's going to look a little bizarre to you, but you'll see trig next year in the spring, and then this stuff will be no big deal. So we could set up two ways of doing this. We could like decide we're going to calculate the angle we'll do a function of two variables here by inputting values for the range and the velocity, or we could, if we wanted to, we could select a velocity based on the range and the angle. Let's start off, we were playing this game. We wanted to pick an angle, right? So all I have to do is just use this formula, let's see, right here. Just that formula right there. Okay, well, what are the odds? I just happen to have that in Desmos. So let's use Desmos to do this calculation. We don't care about the graph at all. We just want to use, I'm just going to use that function to make some predictions. Okay, so where were we? We were looking at, let's see, where was that? Was it? Was it on there? No, where was that thing? Was it that one? Third one, that one? Oh yeah, you're right. Yep, you got it. Yep, it was bundled with, oh, there we go. Okay, so here's our initial speed. Oh, let's see, we said the initial speed was 22 and the angle was, tells us up here, 85, right? Or no, sorry, the range. We're gonna calculate the angle. The range is 21.5. Okay, so let's put that stuff into our function and see what we get. Okay, so we're going to use the function f, and we're going to input x first. So the x, that was 21.5, right? We're calling that the range. Yep, 21.5. And then we were inputting a speed of 22, and so it calculates an angle of about 77 point, and some change. So we'll just round it to 77. Let's see how we did. Let's see. Oh, what do you know? Okay, math wins the day. Okay. Well, let's try this a little differently. Let's reset everything. And let's pick a speed, somebody. 19. I heard 19 first. We're picking 19. Now pick a range. One picks up, say it again. Like, say it again. 6 for the speed? Okay, we can do that. Okay, this is going to be kind of boring. 6 for the speed. What are you going to do for the, now the range? Well, I don't know if it can, I don't think it can make it to 30 with that speed. We got to make the speed a little higher. What is it? 7? I heard 30. Can I go to 30? We'll go all the way to 30. How about that? And the range we wanted to be what? Okay, we'll make it really close. You pick. What do you want it? 6? Okay, that's fine. We'll pick 6, okay. 6.7, okay. No, I'm not doing 6.7. Pick a different one, because we'll do 6.5. I like that one a little better. 6.7, oh my goodness. Okay, so now this time we want to pick, actually, I'm going to let you guys, we're going to do this differently. This time we're not picking the speed, we're picking the angle. And we're going to choose the speed based on the angle, right? We're going to mix it up a little bit. I don't think it'll go that low. I think 80. Okay. Okay. Well, first of all, let's see if this will even work. Like if I shoot at an 80-degree angle with maximum speed. Yeah, it goes pretty far. Goes pretty far. So we're good. It's way over the target. Okay. 89 degrees? It will. Okay, we can't do that because it won't go far enough. I'm going to pick 80. So now the point is, now we've got to pick, you guys have to pick the speed that's going to make this thing hit the target when the angle is picked. The angle is 80 and the target is 6.5. So you pick the speed. What do you think? 10. Okay, we'll try 10. Oh. 22 I heard. Let's try 22. Tell you what, you had your chance. We're going to let math do it for us. Okay, so we're going to go up here and we're going to use the function g, right? Because we can also, if we want to, going back to all this stuff, we could go up to this step up here and we could solve for v if we want to. Letting x, delta x, we're just calling it x, be a variable and theta be a variable. Okay, so then that gives us, if we do that, it gives us this formula right there. Okay, so we'll use that one. So G of, let's see, what is it again? We want to put in X first, so that's 6.5. And then we're putting in theta, and I haven't checked this, so I hope I did it right, which is 80. It says 13 point, oh, it's kind of right in the middle, 13.6, so we'll round up to 14, how about? Hey, what do you know? Okay, again. So math is amazing, right? Math makes accurate predictions for us. Okay, while we're playing with this, maybe we'll just do one more quick thing. How about if we take a look at, yeah, this is kind of fun. We'll take a look at this one. So here's just another mathematical model where the equations are already programmed into this. So it's a pretty simple equation if we're not including air resistance. So like if you wanted to figure out what the maximum range would be, now my velocities go from 0 up to 100 meters per second. So let's take an initial velocity of 100 meters per second. And if I let my angle be like 30, let's see what happens. If I fire this thing, that gives me that's the trajectory, okay? What if we move this thing up to 45? That would give us the maximum range. And we can go out there quite a ways. We go out there over a kilometer. Okay, if we fire this at a 45-degree angle with 100 meters per second initial velocity, what do you think is going to happen if I do include air resistance? Not go as far. So make a prediction. How far do you think it's going to go if I take, and let's pick, what are we using here? We're using a, does it tell us? I thought we could kind of pick what we chose here. Maybe not. Thought we could. Maybe I got the wrong one. What do you think is going to happen to our projectile? Let's see. Is there a way to? I think there is a way to do this. Okay. Yeah, I can pick the drag parameter. So you guys pick. What do you want me to use? How about a tennis ball? We'll use a tennis ball. Okay, tennis ball, so something like, yeah. Okay. All right. So this is for a tennis ball. How far do you think this thing is going to go? Not far. Like instead of a kilometer, how far do you think it'll go if I shoot it at 100 meters per second? Now that's pretty fast. 100 meters per second is, I mean, that's like, 330-ish feet per second. That's pretty fast. Only a little bit. So make a prediction. How far do you think it's going to go? What did you say, Jerry? 700. Okay. Any other predictions? How much? 800. Okay, in that range. Let's see how we do. Oh, I think I messed this up. Hang on. I don't think. Oh, I didn't turn on. Oh, I see. I see what it's supposed to do. Hang on. I got this wrong. It's supposed to go like this. Yeah, I got you. So it's supposed to be like that. Okay, here we go. Not very far. 100 meters. So the air resistance changed things quite a bit, didn't it? Okay. That's a much, much more complicated model, but we could make those predictions too, right? But that requires, college level, undergraduate level calculus. You have to solve some differential equations. But the math models will tell us exactly what's going to happen. Okay, so I made my point. Math models are awesome. They work. Okay, but sometimes they get, we run into situations where we have to do something different. We have to set up the whole function in a completely different way. Like, what about this one? What if we wanted to model a more complex situation like this? So you're visiting the beach at sea level, and you hitch a ride on a hot air balloon that rises vertically to an altitude of 15,000 feet, at which point you bail over the side of the basket with a parachute. You plunge downward until you reach an altitude of 3,000 feet, where you pull the ripcord and you deploy the parachute, and then you float down peacefully to the beach. Okay? Can you come up with a model that's going to work for that situation? Do you see a problem? Like in that previous example, it was pretty straightforward. With a little trig and some algebra, we were able to come up with a model. I promise you, and again, it seems complicated, but it's really not. That was pretty easy to do. What's the problem here, though? How am I going to get a model? What do you think? There's no angle or speed, and there's something else going on here. Okay, we don't have a time yet. I mean, we could probably calculate that, but what about this situation is fundamentally different that's going to make it a lot more complicated? Say that again, Tim? Okay, well, I mean, we're going to count the ride up too. So we're starting at sea level, and we're going to start the stopwatch at sea level, and then you're going to travel up to 15,000 feet and back down, right, during some period of time. But what about this is making it really complicated? Yeah, it's not a constant velocity. I mean, it's changing a lot, isn't it? Wouldn't you agree there's going to be some distinct parts of this whole trip? Like, we could call them chapters. Like, what's chapter 1 going to be? Well, yeah, going up, right? So chapter 1 is you ride upward. Okay, maybe that takes, that might take a while because you're going up pretty slowly in that parachute, and we're going to say we ride up at some constant speed. Maybe that takes an hour to get up to the elevation, depending on how fast we go. What's the next chapter? Very different. Yeah, you bail out over the side, right? And so you're accelerating downward. Do you accelerate the entire way? You don't, actually. Yeah, you don't. What happens? But we're not going to deploy the parachute until we get to 3,000 feet. Do we accelerate all the way down to 3,000 feet? Kind of imagine yourself now. Put yourself in this position. You got your parachute on and you bail out over the side. And that's going to take a little while to fall from 15,000 feet to 3,000 feet. Do you accelerate the whole time? Does your speed keep increasing? What happens there? I bet you have a sense of this. Okay, what do? You hit terminal velocity. What's that? I bet you got to take physics when you're juniors or seniors. Physics is the greatest thing you could ever study. Terminal velocity, talk to me about that. I bet you have some idea what that is. What does that mean? And then you hit terminal velocity is the fastest that you can fall, right? I mean, you finally hit some top speed and you stop accelerating. You can change that, by the way. If you're falling kind of horizontally, your terminal velocity, I can't remember what it is, but it's, 120 miles an hour or something. But if you dive, you can go a lot faster because you're more aerodynamic, right? What happens at terminal velocity? Why do you stop? Why do you hit some speed and you can't go any faster? Say it again, Evelyn. Okay, so gravity's pushing you down, trying to accelerate you. How come you're not accelerating anymore? Okay, air resistance is pushing you up. And when you get going fast enough and that air resistance builds up to a high enough force, the two balance each other out and then you don't go any faster, right? Okay, we can look at, you're pretty lucky that we have air resistance too. Just a little more fun with Desmos here. If we want to look at what would happen if there were no air resistance. Let's see, we want to fall from 15,000 feet. So let me set go up here to like, okay, so yeah, if we look at this, the velocity as a function of height. So we want to know what's our terminal, how fast are we going to go based on how high we start off, right? When we hit the ground, if we didn't have a parachute, how fast would we be going based on our starting height is what we're graphing. Ooh, I gotta change y a little bit here. So negative 100, maybe up to like 500. Ooh, it's not even close, huh? Okay. Well, if we started at 15,000 feet, let's graph that line. Let's see, it looks like we would have a velocity when we hit the ground of about, what units am I using here? I think I'm using feet per second. So we'd be hit the ground at about 668 feet per second. That's pretty fast. How fast is that? What percentage of the speed of sound would that be? Let's look here. What percentage of the speed of sound would that be? That's oops. Okay, that would be about 87% the speed of sound you would hit the ground at. What percentage, like if we take like a handgun bullet, what compare it to that? It would be, yikes, it would be about 34%, 134% of the speed of a handgun bullet. That's how fast you'd hit the ground if you bailed out without air resistance. So fortunately, that's not what happens. Fortunately, air resistance slows you down quite a bit. So, yeah, you would not accelerate forever. We only accelerate for about 12 seconds. That's it. Only for about 12 seconds. And then you hit terminal velocity. Okay? So think about that. We got 3 chapters already. We ride up to the 15,000 feet, we accelerate for a while, we hit terminal velocity, and so there, I've forgotten this, but about 120 if you're horizontal, about 180 if you're diving, and we fall at a constant speed for about a minute. About a minute you would fall if we're horizontal, let's say, till we hit 3,000 feet. Then what happens? Okay, so imagine this. Yeah, you're falling pretty fast, 120 miles an hour. What are you going to experience when you're falling down towards the ground and you pull that ripcord? Okay, yeah, you're going to experience a pretty big force in what direction? Yeah, it's going to be, right, because the air resistance is all of a sudden going to increase, and it's going to accelerate you up, or you're going to get pulled upward until you slow down to your new terminal velocity, which is about what? What do you think with a parachute? I don't know. Slow enough that you can easily survive, though. Okay, feel a strong upward acceleration, rapidly slows your descent, and that takes about 3 seconds to slow down. And then what's the final chapter of our story? Yeah, you just kind of float down to the ground, right? From 3,000 feet, it takes about 2 minutes. How are you going to manage to describe that journey? That's 5 very distinctly different chapters. If you wanted to have a function that gave you your altitude as a function of time, There is no way you can find a single continuous function that's going to do that. There are no math functions that would model that well. There's some complicated things we can do using like Fourier analysis that would give us one that would be pretty good, but it's not going to be perfect. So we've got a different mechanism in math though. We have a new kind of a creature called a piecewise function that does the job. A piecewise function is just a function that breaks up a function into two or more individual pieces, each with their own like domain, right? So the input values would be prescribed for each of those chapters, right, or each piece. Like for example, the domain of chapter 1 for our balloon ride it lasted 1 hour, right? So those were the input values for time that would have applied to chapter 1. Chapter 2 is pretty short. We only have a domain that's only going to be from 1 hour to 1 hour and 12 seconds would be the domain where we're in chapter 2, where we need a different function. From 1 hour and 12 seconds to 1 hour, 1 minute and 12 seconds would be in chapter 3, which would be maybe a completely different equation that would describe that motion, and so on, right? Well, let's look at this in a little simpler case. Let's look at this with just a math equation. It's a little bit simpler, right? This just involves a piecewise function with 3 pieces. All of those pieces are just linear equations, so they're things we can deal with pretty easily. How do we write these things? Well, notice how the notation is. When we write a piecewise function, we've got function notation, so f of x equals, and then we've got just one of those script brackets, only one. One of them that opens to the right, and then that's going to give us room to write rows for each of the pieces of our piecewise function. So how many pieces does this piecewise function have? 3. So there are going to be 3 different behaviors in this function. We should expect the graph to have 3, we should see kind of transitions between those behaviors. So the first behavior we'll call the red behavior. That is where the function has the equation y equals 2x. Okay? Where am I going to graph that? Because that function is only going to exist for specific input values. So for which input values of x is an ant that's walking on this piecewise function going to be walking on the red piece of the piecewise function? Yeah, less than or equal to -2, right? So anytime I have an x value that's less than or equal to -2, if that's where the ant is in the xy plane, that ant is walking on the red piece of the piecewise function. Okay? Well, what happens is that ant is walking to the right, so his x values are increasing, and the ant steps from x equals -2 to, for example, -2 or -1.9. What happens to the ant? Okay, now he's moving from the red piece onto the blue piece, which is a completely different equation, right? The equation of the blue piece of the piecewise function is y equals -1 minus x, so a different line, right? So the ant's going to continue walking to the right along the blue piece until he gets to what value? 4, right? Once the ant gets to 4, when he actually steps on 4, well, it looks like 4 is included in the green piece of the function. Then all of a sudden the ant moves, he steps onto a different part of the graph, onto the green part of the graph, which is the line y equals -3. And for all values of x greater than or equal to 4, the ant would just continue to walk on that green piece of the function, right? Okay, you kind of get an idea of the flavor of this? Okay, so what are our goals here? Well, we want to do a couple things. We want to know how to evaluate a piecewise function. And let me see, did I include? Okay, I think let's just try, before we do anything, let's just try to evaluate this function. So what if I wanted to calculate the output value when I'm inputting, let's see, how about if I'm inputting -1.3? How would I do that? Evaluating just means I'm plugging in an x value and calculating the output value, the y value, what would I do? Okay, so if I'm plugging in a value of negative 1.3, in which domain are we? Are we in the red domain, the blue domain, or the green domain? And what's domain? I keep throwing out the word domain. Remind me, what's a domain? The set of all the inputs, right? So we're throwing out an input value of negative 1.3. Well, which domain are we in? Which set of input values would that apply to? Red, blue, or green? Yeah, right? Because negative 1.3 is greater than negative 2 and less than 4, right? So that's going to be a blue value. So I would plug negative 1.3 into the blue function. So I'd get negative 1 minus negative 1.3, which is what? Yeah. That'd be like negative 1 plus 1.3. So I just get 0.3. Make sense? Okay. What if I wanted to evaluate the function at negative 10? I'd plug it into the red domain, right? Everybody see that? So you have to choose the piece based on the domains of the pieces when you input a value, okay? So evaluating them, no big deal, right? You just have to be careful to determine the input x value fits into which domain. Okay, how do we graph this thing though? How about that? So if I want to graph this, let's start off with dividing up the domains. Okay, so the first thing I could do, wouldn't you agree that we have transitions from the red domain to the blue domain at negative 2? Give me thumbs on that. Everybody see that? And we transition from the blue domain to the green domain at positive 4. So let's just create some vertical lines which are not part of our graph, but they're useful because they're dividing up the xy plane into 3 regions, right? We've got the red region, which is all the x values less than negative 2. So that's going to be everything to the left of that vertical line, right? It's going to look like that. That's my red region, okay? I want to graph the red function in the red region, but that's the only place where it lives, okay? So in that region, the equation I'm graphing is just y equals 2x. Okay, so how could I do that? That's the challenge for you. How could I graph the red line, it turns out, that's all it is a line, in the red domain? It'd be easy to graph that line if we were just graphing y equals 2x in the xy plane. What would you do? I mean, it's in slope-intercept form. What's the slope? 2, right? And what's the y-intercept? 0. So we would just start at 0 and rise 2 and run 1, right? What's the problem with that now, though? Yeah, that's not the domain, right? If I plug in 0, I mean x equals 0 in my function, that's in the blue domain, not the red domain. So that's not going to be a strategy that works well for us. What else could we do to graph it? How do you graph a line? 2 points, right? We just need 2 points so that we could connect and extend. So what do you think, Hayden? You got an idea? Okay, yeah. How about if we find 2 points that are in the red domain? Like for example, one that we definitely want to choose is probably negative 2. So we know where that line ends when it gets to the edge of its domain, right? So what if I plug in negative 2 into my function? What do I get for y? Negative 4. So we'll just make a little t-table. And we'll plug in the value negative 2 and we'll get back negative 4. And remember, those are just the ordered pairs of a point, right? This is an ordered pair corresponding to a point. And so we end up with what kind of a point? Is that going to be an open or a closed point? It's closed. How come? Okay, because negative 2 is included in the domain of the red piece of the function. All right, so we'll go ahead and drag. I've got some ready-made points here. So -2, -4, we said. Let's drag a point up here to -2, -4. There it is. There's one point. And then I need one more point, right? So, I mean, we could pick any x value we want that's less than -2. So for, like, what would be some examples? -3. Why not -3? So if we pick I picked -4, I guess. Doesn't make any difference. If we pick -4, what do we get for our output? -8. Okay, so if we go back to -4, -8 puts us right there. And obviously that's going to be a closed point because it's inside the domain. And then what do? Well, I just connect and extend those points. Okay, so we would just... So there's the red piece. And it's just going to go on forever like that. Okay, give me thumbs. Does that make sense? Okay, good. All right, so next. What do you think we're doing next? It's the blue piece. There you go. Okay, so we move on to the blue piece. Got our red piece graphed. Now we need to graph the blue piece. Okay, so in its domain, suggestions about, we're going to use our t-table to just create 2 points to define our line segment, right? Just to give me a piece of a line. What x values would you recommend using here? 0 you could use, yeah. And I get that. Anybody have any other ideas? Could use 1. Okay, I'm going to say -2 and 4. How come? Okay, because those are the boundaries, right? Those are the edges of that region. Is -2 included in the blue region? No, it's not, but every point greater than -2 is included. And so I could still use that, but what kind of an endpoint would I need? I would just include an open endpoint, right? Okay, so what happens if I evaluate the blue function at -2? Well, what do you get? Because we're using, so now we're in the blue region, which is the equation, whoops, I want to be blue. Y equals -1 minus x. So if I'm choosing -2, what do I get? +1, yeah. -1 minus -2 is like +2. Yeah, so that would give us the ordered pair -2, +1. Okay, there's an ordered pair. And you guys correctly told me already we want an open endpoint there. Okay, so we'll do that. -2, +1 is right there. What other one would we use? How about 4? Is 4 included in the blue region? No, so what kind of endpoint? Open. If I plug 4 in, what do I get? -5. -1 minus 4 equals -5. So we got the ordered pair 4, -5. So over 4, down 5, right there. And then all I have to do is just connect those points, right? Because it's a line. So those 2 points define the line. Okay. There it is. Okay. Give me thumbs. How we doing? Make sense? Okay, what's next? The green region. Yeah. Okay, the green region's pretty easy. What's the equation of the line in the green region? Y equals what? Y equals -3. What's that look like? Show me with your arms. Yeah, that's a horizontal line. That's an easy one, right? So that one, we can kind of take a shortcut. We don't even probably need a t-table with that one. We're just going to get a horizontal line starting at x equals 4. So is 4 included or not included in the green region? It is included. So we're going to use a closed endpoint. And we've got the line y equals -4. Negative 3. Whoops, negative 3. You're right. Okay. Oh, I wrote that wrong, didn't I? Yeah. Okay. And so we've got our endpoint right there, and then we're just graphing horizontal line that just does that. And we got it. That's our graph of our piecewise function. Okay. So what's it look like? There it is. Okay. All right. So next, we want to write what's the domain and the range of this piecewise function. So remember, the domain is the set of all the possible input values. So let's do a projection here. You remember projections? We talked about projections. What was a projection again? Remind me. Like a projection onto the x-axis, let's say, because that's going to be the domain. How did I do that? Okay, yeah. It's like shining a light from above and below, and it's the shadow that the function casts on the x-axis, right? Alternately, we could think about just squishing the entire function onto the x-axis, and what would I end up with if I took all those infinite points and just smushed them vertically onto the x-axis? Yeah, it's the entire x-axis, isn't it? Everybody see that? So the domain, if we graph the domain in orange, the domain just looks like that, right? So what is the domain? Just all reals, isn't it? Yeah, because those are the x values. What if I wanted to write that with interval notation? What would it look like? Yeah. Okay, what about the range? Let's make the range purple. Okay, what about the range? Let's take it piece by piece. What's the projection of the red piece onto the y-axis? Okay, so it's gonna go all the way up from negative infinity up to negative 4, and it stops there with a closed endpoint. Everybody agree? That's the projection of the red part. Would look like that. How about the projection of the blue part? Okay, it'd go from 1 down to negative 5. Well, part of that's already shaded, right? So the only thing we're going to be adding to the projection from the red from the red function would just be this little part that sticks up. What kind of endpoint am I going to have? Open, okay. And then what's the projection of the green graph onto the y-axis, right? Because we're doing the range. It would be only at one place. Where would it be? Yeah, if I project this whole thing, squeeze it onto the y-axis, it only creates one point that's already graphed. So there's all three of them combined. So based on that graph, can you tell me what the range is? How about writing it as an inequality first? Y is what? But I want to say it as an inequality. Y is less than 1. I agree, right? Less than 1. So if I wanted to write that using interval notation, what would that look like? Yeah, there you go. Okay, makes sense? And we're just looking at an interval again, like we've been doing with interval notation, only now we just have to look sideways, right? Okay? All right, it's a good place to stop. Give me 1 to 5 on that. Is that making sense? Okay?